Okay, I think we'll go ahead and get started. My name is David Castor, and thanks for joining our webinar session today. We're going to talk about molded case circuit breakers. That's a circuit element that we use a lot, and it's probably our most common protective device. So I think it's worthwhile to spend a little bit of time just going over the basics. It'll probably be a review for a lot of you, but we'll talk a little bit about what makes up molded case circuit breakers and some applications and some special conditions related to that. Okay, we'll see if we can get going here. So just a little history of molded case circuit breakers. Back in 1904, a company called the Cutter Manufacturing Company produced what we would think of as the first circuit breakers that had a inverse time function, and they called it the inverse time element breaker, or ITE breaker. And that became so synonymous with the company that they eventually changed their name to the ITE company. So those of you of a certain age who still remember the ITE company, that's how it got its name, was the inverse time element function. And so back in 1925 then was the first National Electrical Code revision that required circuit breakers to be enclosed and externally operable, so getting away from the knife switches and exposed live parts. So that was the trademark of the molded case breaker. And then in 1932, Westinghouse came out with what you would recognize basically as a modern molded case circuit breaker. Probably the last major advance was 1973, which was the first electronic trip unit that was put out. That one was, of course, an analog type device. Now all the new ones are digital. So just a little background on molded case breakers. So if we look at a typical molded case circuit breaker, they have a lot of commonality. They were built to the same standards, so there's a lot of similarity between the devices. And it's definitely become a mature product over the last 100 years. So fair degree of consistency from manufacturer to manufacturer. So basically you have the case or the frame, that's the molded case, which is an insulating material. You have the terminals, obviously, the line side and the load side. There are restrictions about reverse feeds on the breaker and how they're mounted, so that's something you need to look into. If you want to mount it upside down, it has to be rated for that. Also, if you want to feed power from the load side through the line side, that also has to be specially rated. So that's reverse feed. The breaker has operating mechanism, which is the handle, the trip handle is in the front of the breaker that opens and closes the contacts. It has a trip bar, which is what the tripping mechanism actuates to trip the breakers. And it has contacts that actually carry the current open and close and when the breaker operates. And in this area up here, these are the arc chutes or the arc extinguisher. The breakers all work by opening the contacts, creating an arc, and then we have arc extinguishers that exist to break up the arc and extinguish it to get to current zero. I should mention that we will be putting a link on the website. We're recording this session, so you'll be able to pull up a recording of this in a few days after we get it posted on our website, so it will be available. Okay, so in terms of the standards that molded case circuit breakers are built to, that's just going to vary depending on which country you're in. In the US, the dominating standard is the UL 489, and that's going to cover virtually all types of molded case breakers, and it's very well harmonized and consistent with the National Electrical Code. So when we get into the 80% continuous ratings and 125% continuous loads, the conductor sizes that you end up using for the breakers, then it's very consistent with the requirements of the National Electrical Code. UL 49 is not a free standard. You would have to buy that, and it's quite it's a big standard. So, but the requirements, you can usually get access to the basic requirements in UL 49 from the different manufacturers of breakers. There are two free standards from NEMA, AB3 and AB4. AB3 covers the application of molded case circuit breakers, and AB4, which we'll talk about in a little bit later, talks about field inspection and testing of molded case circuit breakers. And that becomes, if you look at a molded case breaker, you can't really tell what's going on inside, and so it becomes a little bit difficult to tell when they need to be replaced. So AB4 gives you some guidance on that, and there's another IEEE standard that we'll mention here at the end that also aids with for field inspection and testing of molded case circuit breakers. All right, so if we look, we're going to start with a discussion of the typical thermal-magnetic molded case circuit breaker. And this is a purely electromechanical device. It doesn't need any power, has no electronic components in it. The molded case circuit breaker, thermal-magnetic breaker, is really two different protective mechanisms built into the same device. They have a thermal element, inverse time for low-level faults and overload conditions. And when we say inverse time, all that means is that the higher the current, the faster it trips. So the tripping time is inversely proportional to the fault current. So the thermal curve, the thermal element protects against low-level faults. Then we have a magnetic trip, and that's the instantaneous trip. It's not quite instantaneous, of course, but that's for the high magnitude short circuits. That's your fault protection. In the larger breakers, the magnetic trip is going to be adjustable within a certain range, and that range is governed by the UL requirements. So there is an upper limit for molded case circuit breakers where they have to trip, have to have instantaneous trip at some point. And so we'll talk about that a little bit more as we go along. So I borrowed an image from an old Westinghouse book I had on molded case breakers. This shows the thermal element. So if you look down at the bottom diagram, this is the normal operating condition. So you have the current path goes through the contacts, up around here, down this way, and back out to the load. There's a bimetallic element, two different types of metal that have different thermal expansion characteristics. As that bimetallic strip, this is similar to what you see in motor overload relays. Maybe you're familiar with those. As that strip warms up, it starts to bend because of the different thermal expansion characteristics. Eventually, if you look up here, it bends over so far that this little striker bar is going to contact a trip bar, push it, and cause it to release the latch, and then the contacts will spring open. So that's the thermal element inside the breaker. So again, it's an inverse time characteristic. The more current produces more heat, the faster it trips. So this is protecting against low magnitude faults, maybe arcing faults. Unfortunately, you'll find out that's not necessarily a good thing for your incident energy. Also, serious overloads, it would pick up eventually and protect you. Now, in the thermal-magnetic breaker, this is going to be sensitive to ambient temperature. There's some various schemes developed over years to compensate for that, but it is basically a physical thermal device, so the hotter it is, the faster it's going to operate. So you have to keep that in mind, and that limits the application of the breaker. So we have maximum temperature limits for circuit breakers, in part because of this thermal element. The hotter the ambient temperature around the breaker, the more likely it is to trip on an overload. All right, as far as how the thermal element has to work and what the requirements are for that, we can look at the UL requirements. And this basic one may surprise you a little bit, but in a molded case circuit breaker, UL listed breaker, that breaker must carry 100% of its rated current continuously at 40 degrees C ambient But the kicker is that's in open air, which you're never going to encounter in your actual applications. So if I have a 100 amp breaker mounted in open air, it should carry 100 amps continuously forever without tripping. That's the one basic requirement. The second basic requirement is at 200% of the rated current, it has to trip within the maximum times given in the UL standard, and there's a table. It varies depending on the breaker size. So just to give you an idea of what the requirements are, up to 30 amps, the breaker has to trip in 2 minutes at 200% current. So if I had a 30 amp breaker, it would have to trip at 60 amps current, it would have to trip within 2 minutes. That time increases as the breaker rating increases, just due to the bigger mass of the thermal elements. And so eventually when I get up to a 100 amp breaker, it's 6 minutes. When I get up to a 2000 amp breaker, it's 28 minutes. So that's the basic UL requirement that every breaker that has a UL label has to meet. All right, so let's talk now about the magnetic trip. That is basically like a solenoid, an electromagnet that the current passes through. Again, from this old Westinghouse diagram I borrowed, we have the line current passing through this coil and then out to the load. And eventually, if the current's high enough, there's enough force created by this electromagnet that it's going to pull this element in, which causes the breaker then to trip. The last latch is released and the contacts spring open. So this basically will not trip until you get above a certain current, and then it trips immediately with no intentional delay. So its purpose is really to detect faults, short circuits of high magnitude. In the larger multi-case breakers, this is going to be adjustable, and the smaller ones, such as you might have in your house, it's non-adjustable. And the instantaneous pickup is defined as a multiple of the current rating is defined in the UL 489. The other thing to keep in mind is that this solenoid, this electromagnet, will respond to DC as well as AC current. So it's going to see the asymmetrical current. So that becomes an issue if you're trying to prevent nuisance tripping for motor starting. You have a DC offset in the inrush current, transformer inrush. So those kind of things cause you to maybe have to go to a larger breaker size than you might like, particularly for transformer primary protection. So if you size your primary transformer breaker strictly based on the transformer full load amps, you may find some nuisance tripping issues because of the inrush in the transformer. So when the breaker trips on its magnetic trip, instantaneous trip, the fault clearing is generally very fast. Typically, 1 cycle, 1.5 cycles, 2 cycles, something in that range. It's extremely fast. And it's this magnetic trip that causes the Arc-Flash levels to be low when the bus or equipment you're looking at is protected by a multi-case circuit breaker that's upstream, because they trip extremely quickly. And so almost regardless of how much fault current you have, you're going to have relatively low Arc-Flash incident energy if your upstream multi-case circuit breaker is tripping on instantaneous. Keep in mind that the multi-case circuit breaker per UL 49 must have instantaneous trip. This is to protect itself as much as anything else, right? It's not rated to carry fault current, does not have a withstand rating, can be tested for that, but eventually there will have to be a instantaneous trip at some level. The fact that you have all these multi-case breakers with instantaneous trip can create coordination problems when you have these in series, and we'll look at an example of that a little bit later. Okay, so that's the magnetic trip. The thermal trip we talked about. You put the two together and you get the time current curve for a typical thermal magnetic breaker, okay? Now, if you're not familiar with the time current curves, keep in mind that this is a log scale. So down here is 0.01 seconds, 1 second, 10, 100, and 1,000 at the top. So 1,000 seconds is like, what, 16.6 minutes, something like that. So we're not seeing the very long-term curve here for the thermal element. So really you have two completely different protective devices built into the same device. You have the thermal element. This is the inverse time, this curve here. So as the current increases, the faster it operates. Then down here you have the magnetic trip or instantaneous trip. You can see for this particular breaker it's just over 0.02 seconds, which is just a little bit over a cycle. One cycle is 0.0166. This vertical line here is really this is with the instantaneous pickup point. So once the current reaches this band here, it's going to be, the breaker is going to trip on instantaneous. Now there is this thickness of this line, this width of this band is the tolerance for the breaker. So if the fault current is right inside of that band, you don't really know if it's going to trip on instantaneous or if it's going to trip on thermal. So that's just an inherent tolerance of the device that you have to live with. So the basic way to look at this is that the narrower these bands, the more accurate and repeatable the device is. So. Okay, so this is a typical thermal magnetic breaker curve, and this is actually a generic breaker from the EasyPower library. If you are building your models in EasyPower and you go to the molded case breaker tab, by the way, when you're inserting your low voltage breakers, it's important to first pick the class here, because if the default is typically low voltage power circuit breaker, and if you're looking for a molded case breaker, you're not going to find it until you change it to molded case. But at the very top here in parentheses we have the generic type, and we provide a generic thermal magnetic breaker with time current curves up through 1200 amps, and the time current curves are consistent with the UL49 requirements and also are consistent with IEEE 1584 for Arc-Flash calcs. In IEEE 1584 they do provide some guidance for situations where you cannot identify the type or brand of a particular molded case circuit breaker. And if you've ever done data collection in an old facility, some of them are just kind of this black piece of plastic that you can't really distinguish the manufacturer or much less a model number. So the generic breakers are useful in the design phase where perhaps you don't know what manufacturer you're going to get, and also in situations where you just are not going to be able to determine exactly what model breaker it is. So the curves that we have in the generic, the TCC, should be conservative. Also, if you use the auto design, smart design in EasyPower, we have the default is a generic design sheet which will put in generic breakers. So you can use a generic breaker when you're just quickly trying to build your model and you don't really have a particular manufacturer in mind, and that's going to work up through 1200 amps. So a special type of molded case breaker that we deal with quite a bit is the motor circuit protector, or magnetic only breaker. The motor circuit protector is actually, I believe, is still a trade name of, was Westinghouse, Cutler Hammer and Eaton. It's a magnetic only breaker, so it has no thermal element. And you can see this is just the instantaneous trip. And the instantaneous trip is actually way down at the bottom here. This little thing here is the instantaneous trip. The vertical line is the instantaneous pickup. So these are used as part of a combination motor starter where you have an overload relay that's going to provide the overload protection for the motor. That's the only place these can be used. Has to be a listed combination motor starter. You cannot use the MCP or mag-only breaker as a feeder breaker. And we do see this fairly often when we do data collection. Somebody has cannibalized a motor starter and used that breaker as a feeder breaker. And you cannot do that because there's no overload protection. So we do have these in EasyPower. They're under molded case breakers. It still calls them a thermal-magnetic, but if you call out the proper model in EasyPower, then it'll generate a curve like this, just the instantaneous only. And the instantaneous pickup here is always adjustable in the motor circuit protector. All right, so why would you want to use, this is just an example. In EasyPower, we will attempt to combine the MCP curve with the thermal overload curve and into one curve. And so this is defined in the data for the breaker. So let me just, I'm going to jump into my EasyPower model here quickly. If I look at this breaker here, if I double click on it to pull up its data, it's an MCP, which is going to be a mag-only breaker. You'll see, just to point out one of the advantages of the MCP, it has multiple, for the same frame size, it has multiple models that have different adjustable trip instantaneous range to handle a wide range of motor horsepowers and inrush. So you do have quite a bit of, and then for each of these frame sizes, then there'll be a range of adjustable trips that you can pick. And EasyPower will show you what the setting is. So if I change this from I to H, that goes down to what the actual pickup setting is. And that's going to be the nominal pickup. But if you do want to model the motor overload time current curve, you just go to the motor overload tab and check this box and define your motor overload relay here, and you'll have to enter the motor full load amps and the service factor. So if you do that, let me pick this, I go to plot here, then I get, let me shift that over. So here's my magnetic only breaker combined with the motor overload relay into one curve. So if I double click on this, if I go to the motor overload and uncheck this box, the plot box, and say apply, then I just get the MCP curve. So in EasyPower, that motor overload data, if you want to show it, is defined under the breaker data. And again, even though it's mag only, up here it's going to say thermal-magnetic, but EasyPower knows that it's a mag-only breaker based on your specification. Okay. Again, just a slide showing how the motor overload data is defined in EasyPower. So why would we want to use MCPs instead of something else? So you can also use thermal-magnetic breakers in your starters. You can also use fuses. Well, if you buy a thermal-magnetic breaker, it has to meet the UL requirements for feeder breakers. It's only available in certain sizes, and the instantaneous trip has to be within a certain range. Because the motor circuit protector is a special application, it's allowed a much wider range of sizes and trip adjustments. And so you can get fine-tune your instantaneous trip to the motor, locked rotor, and inrush current much better than you can with a thermal-magnetic breaker. And the MCPs, at least according to the manufacturers, have specially designed trip coils with some built-in transient suppression to help deal with this issue of the extremely high inrushes we see these days with energy efficient motors. So in terms of comparison with fuses for motor protection, if you look at typical motor faults, they're usually not a solid bolted fault. There's some fault impedance in there which kind of limits the fault current. And so a fuse will tend to be slower than the MCP for most of the typical motor faults that occur internal to motors. That's maybe some bias there, that test data comes from the circuit breaker manufacturers, but it does seem to make sense that if you have extremely high fault currents, like a bolted fault, the fuse is going to be perhaps faster than the breaker. And the fuse probably can have a higher interrupting rating. But for typical faults that you actually see in motors, the MCP can tend to be faster than the fuse. All right, so we've been talking about thermal-magnetic type molded case breakers. And we're going to talk now a little bit about the solid-state trip units. So in what we call a solid-state trip unit, that bimetallic strip and that solenoid for instantaneous trip has been, for the most part, replaced with nowadays a digital microprocessor and current sensors. And so the waveform is sampled and digitized, and then there's some numeric processing that occurs, and similar to the trip units on low voltage power circuit breakers or digital protective relays. So the tripping mechanism and the arc chutes and all that, lugs and everything is pretty much the same. It's just really the sensing and overload and short circuit tripping sensing is different in the solid state units, obviously. The advantage is that you get much more flexibility in the settings. They're going to be much more accurate and repeatable than the electromechanical devices. You still have to have instantaneous trip. With the solid-state trip units, it's quite easy to provide ground fault because they simply sum the three phases together, and unless you have neutral current, neutral loads, then it's pretty straightforward to get ground fault protection. You still have to pay more for it, but it's pretty easy to provide. Now what we're seeing is that the solid-state trips are becoming standard from the manufacturer, which probably means with the price of electronics coming down, they're becoming cheaper to make than the thermal-magnetic devices. So I think that trend will start pushing down further into smaller and smaller breakers. So probably some point in the future, all the breakers will have electronic trips. We're going to talk about 100% rated breakers in a minute, and 100% rated breakers must have some type of solid-state trip. All right, so we looked at the time current curve for a thermal-magnetic breaker. Here's a typical time current curve for a large molded case circuit breaker with a microprocessor or solid-state trip. So you can see instead of that kind of big sweeping inverse time thermal element, we have a much more precise curve here. So up at the top, this is the long time. Here we have the pickup setting. Then we have the long time delay band. This may or may not be adjustable. In molded case breakers, a lot of times these are fixed settings. There's a limited adjustment range. Depends on the size of the breaker and how much you want to spend. Down here is the short time trip, this horizontal line here. So there's some delay in there. And this is the short time pickup setting. And then we have the instantaneous trip. This particular breaker, there's a little bit of a range here where the instantaneous trip is speeding up as the current increases. And so I turned off the clipping so you could see what that looks like at the very high levels of fault current. So in addition to the protective functions you get at the solid-state trip, you can also have metering functions. You can get the current readings displayed on the breaker. You can have some kind of communications with the device through a serial connection, so you can get data sent back to the SCADA system or your plant control system is possible as options. So lots of flexibility in the solid-state trips that you don't get with the thermal-magnetic breaker. If we go, I'm going to go back to the EasyPower just for a second, and I'm going to go to my other model I have open here. So I've got basically two identical systems here. The go to coordination focus. These breakers are thermal-magnetic breakers, and these are electronic trip breakers on the left side. So just to give you a comparison, we can look at the main breaker here. They're both 2500 amp breakers. One's thermal-magnetic. This is some kind of a electronic trip. So if I plot those two, you can see the difference here in the curves. I have a limited adjustment. For the thermal-magnetic breaker, I can adjust the instantaneous trip. That's about it. Okay. For the solid-state trip, for this device, I have more adjustment. This is the long time delay adjustment. I believe I can lower it. You can't increase it beyond to 2500, but I can lower it. Down here is the short time delay adjustment. This is the short time trip, and then we have the instantaneous. Okay. So you have much more adjustability, and up in the long time range you get a bit more accuracy in the settings here. With the smaller thermal-magnetic breakers, this thermal band can get quite large. There's a lot of variability in the breakers themselves. Okay, let's talk a little bit about molded case circuit breaker maintenance and testing. This becomes kind of a contentious issue. And the reason is that, a couple of reasons. It's difficult to tell when your molded case circuit breaker needs replacing. Well, sometimes it's not difficult, right? But a lot of times just looking at it, you cannot really tell what the condition of the breaker is. Also, the second issue is that per UL and the manufacturers, the molded case circuit breaker really has no user serviceable parts. If you open the case on a molded case breaker, you void the warranty. And so typically if the breaker has an issue, you have to replace it. Obviously you can take them apart, but it's not recommended. So when we get into Arc-Flash analysis, we find a lot of parts of our system depend on a molded case circuit breaker operating upstream. And so it places more emphasis on breaker maintenance and testing. You go to a lot of old facilities, you test the breaker, it's not functional because it hasn't been operated in 20 years and it's no longer capable of opening. So we'll talk about some of the standards we mentioned that cover assessment of breakers that are in service for inspection and replacement testing. One of the things that's proven useful is thermography, infrared thermography of the breakers to get a assessment of some breaker conditions that can be found that way that indicate the breaker should be replaced. The IEEE, there's an IEEE 1458 standard that's not free, unfortunately, but does cover life expectancy and field testing of MCCBs, and it does talk a bit about thermography, so that might be something you want to get if you're interested in that. In terms of how long the breaker is supposed to last and what it's supposed to be able to do, there's no real clear-cut answer to that. As far as the UL 489 testing requirements, the breaker has to be capable of 2 fault interruptions at the maximum short circuit rating of the breaker. Doesn't mean it can't do more than 2, but it has to be able to do at least 2. So that's just the basic criteria that it has to meet. And again, all the Arc-Flash calculations that we do assume that all the motor case circuit breakers are going to work per their published time current curves. So that puts a little more emphasis and importance on making sure these breakers are actually going to work when they need to work. So I mentioned this NEMA AB4 standard, and it does cover field inspection and preventive maintenance of breakers in the field. I believe that's still a free download if you go to the NEMA website. It's going to basically tell you when to replace the breaker, not anything about repairing them, because they don't consider them multi-case breakers to be repairable. So if there's an issue with the breaker, you just buy a new one. So that's the basis for what's covered in the NEMA standard. So I'm not going to get into detail on that. That's probably another webinar in itself. But keep in mind that there are some criteria for judging when your breaker needs to be replaced. Obviously, if you see burn marks around the breaker on the outside, around the arc chutes or the terminals, that's a pretty good indication. Or if you try to open the breaker and it stays closed, then that's another problem, right? So anyway, you might want to refer to this standard and the IEEE standard I mentioned for more information about how to deal with your actual breakers in the field as they get older and older and older. I want to mention a little bit about the short circuit ratings of multi-case circuit breakers. Like all the low voltage devices, it has a single short circuit rating, and that's based on the momentary network half cycle, and the breakers are rated, the rating is stated in symmetrical amps, but the testing is done at a specific power factor, which translates to a equivalent X over R. And so because the real issue is going to be that peak current of the first half cycle, even though the breaker has a symmetrical amp rating, if your X over R ratio exceeds what the breaker was tested at, that breaker has to be derated for its short circuit rating. Now if you're using EasyPower and the Smart Duty feature, that's all done automatically in the calculation. But just keep in mind that, and we do that by increasing the duty on what shows up in the table. So if you look at the table down at the bottom of the slide, you'll see that's the testing is different at different breaker interrupting ratings. So take 20 Ka and above, the equivalent power factor is 0.2, and that's a 4.9 X over R ratio. You will run into a lot of situations on your larger transformers where your X over R will be greater than that. So there will be some derating of the breaker required. This is the difference between multi-case breakers and low voltage power circuit breakers. The low voltage power circuit breaker is tested at a higher X over R ratio, 6.6, I believe. So there can be situations where the multi-case breaker will be underrated, but the low voltage power circuit breaker would be adequately rated for the same, if they're installed on the same bus. So it is a difference between those two types of devices. So just a slide that maybe sort of illustrates this issue. So the concern is this peak half cycle, this first peak half cycle. And so the symmetrical rating is based on a certain X over R ratio. The higher the X over R ratio in the actual system, the higher this peak is. So if your peak is higher than what they tested it at, we have to derate that. And we do that by increasing the duty amps so we can do an apples to apples type comparison. So yeah, this is somebody had a question about the AIC. Yeah, this is the AIC rating of the breaker, amps interrupting current. Okay, so Also, it's very important that the breaker have an adequate interrupting rating if you're doing Arc-Flash evaluations. You can't really rely on that breaker for Arc-Flash protection if its fault current is exceeded of its rating. So that needs to be factored in. Let's talk a little bit about coordination, selectivity between molded case breakers. So in the most general case, if I have molded case circuit breakers in series, they are not necessarily going to coordinate, even though they have different amp ratings. And that's because of the instantaneous trip. So if my fault current is high enough, all three of those breakers could trip for a fault below the 150 amp breaker there. That's just a fundamental limitation of molded case circuit breakers. So here's two molded case breakers. The purple one is a 100 amp trip, and the one on the right, the blue one, is an 800 amp trip. So they coordinate really well until you get down to the high fault current range down here. And you can see those two curves overlap. Where those curves overlap, that's an indication that they're not going to coordinate. And so if I had a really high current fault, I don't know which one of those breakers will trip first. They could both trip. The upstream one could trip first and not the one downstream. So it's and remember too, once the breaker starts to trip, it's going to go ahead and trip, right? There's no going back. So once you pull the pin, it's going to go ahead and trip, even if it takes longer than if something else has already tripped. So this is the fundamental problem for molded case circuit breaker coordination. But keep in mind that the National Electrical Code does not require devices to be coordinated except for emergency power systems. So if you deal with hospitals, things like that, and you're probably very familiar with the new regulations on selective coordination. And what's happening now is the molded case circuit breaker manufacturers are testing for series coordination between breakers to verify that they will coordinate regardless of what the TCC shows. And that's being done to compete with fuses, which are known to, as long as you have a 2-to-1 ratio between your fuses, they will coordinate just by test. So to compete with that, the breakers manufacturers are now doing testing of their own breakers to establish series coordination. That's going to work up to a certain maximum fault current, basically. So we talk about series coordination of molded case breakers. This is valid only by test, and so when they test it, they will find that the breakers will coordinate even though the curves overlap. And that's going to be limited to certain size ranges. And because the testing is expensive, it's always going to be two breakers from the same manufacturer. So if you've got a Cutler Hammer breaker and a GE breaker in series, there will be no series coordination test data for those two breakers. Pretty sure. So that's another limitation. In this series coordination, there will be a maximum fault current stated in the test data. So above that maximum fault current, they will not reliably coordinate. Now, where we have the data from the vendors, we do track this series coordination and the maximum fault current in the EasyPower library, and we did a webinar on this a year or so ago. So that is, if you're interested in that, you can you'd probably find that on our website, or take a look in the library and see what's there. But you are able to track the series coordination between MCCBs and EasyPower where we have the test data from the manufacturer. Okay, now we're going to talk next about series ratings. That's a completely different concept than series coordination. So they sound similar, but they're completely different, so don't get those two confused. Series coordination relates to selective coordination between molded case breakers in series. I have a question about the recommended coordination time between breakers. Actually, for low voltage devices, the time current curve that the manufacturer provides for the breaker includes all of the tolerances and the operating time and the fault clearing time. So as long as you can see daylight between the curves, between two molded case breakers, they will coordinate. You don't need to add any additional separation. That's not necessarily true for all devices, but for molded case breakers that we're talking about today, all you need is daylight between the two devices. Unfortunately, because of the instantaneous strips, there's not too many of them that where you're going to see daylight all the way along. Okay, so that was series coordination. Now we're going to jump in and talk about series ratings. This has to do with the short circuit ratings, your AIC. So the brute force conservative approach, all the breakers in your system are rated for the maximum short circuit current at their location. This is the sleep well at night approach. But because that gets expensive, if I have to buy 65,000 Ka breakers everywhere, we can recognize the fact that when we put 40, 50,000 amps through a molded case breaker, there is an impedance in the breaker. That impedance is generally ignored in our fault calcs because there's no real good data on it. It's a dynamic value that changes as the fault progresses. But the net result is the fault current downstream of that molded case breaker is actually less than you would calculate. And it depends on what's downstream and a lot of other factors. But if the breakers are tested as a tested combination, you can effectively assign a higher interrupting rating to that downstream breaker than it would normally carry. So you can have a 22,000 amp circuit breaker that has a series rating of 65,000 amps if it's protected by an upstream device that it's tested with. So again, these tested combinations are always going to be two breakers from the same manufacturer. So that's a limiting factor right there. But in certain situations, you can take advantage of this to be able to use lower breakers with lower interrupting ratings at high values of fault current. So the big limitation is these will not coordinate by definition, right? You're definitely sacrificing any notion of coordination at the high levels of fault current to get this series rating. We do track the series rating in the EasyPower library data where we have the data available. So let me go show you where that is, just in case you were wondering. If I go down to one of the little guys here, and go back to database. If I double click on this breaker and bring up its data, it's a GE-TJ4V. If I go to the short circuit tab in my breaker data, the default's going to be this is the interrupting rating. This is the AIC rating that's on the nameplate. We store this in the library. So when you hit calculate, it's going to put the 30, this is in kiloamps, so 30 Ka. That's based on that breaker's own instantaneous strip. If you want to use the series rating, you can check the series box and then hit the calculate button. And it's telling me that says it didn't find a breaker upstream of this device that this breaker is listed as having a series rating with. So this is basically saying thanks for playing, but you don't get a series rating. Now if I had a specific GE breaker here or here that had a series rating with this breaker, then when I check this number would go to 100,000 amps or whatever the series rating is. So we do track that in the library data where the manufacturer has made that available for us. So it's going to default to instantaneous, and you'll have to set it to series if you want to use that. Okay. All right, so oops. Keep in mind that the intent of series ratings was really to use for small distribution panels and circuits where your loads off of this are going to be primarily branch circuits, lighting, and receptacles. If you have motor loads downstream of this downstream device, you can't really use the series rating. So that's because the downstream device will see more current than your upstream device. So that's not an application where you can apply a series rating. So this is not a perfect example, but let's say if I had a fault, say this breaker on this fan and the 3302 upstream, say this had a series rating as a combination. If I have a fault just downstream of this MA breaker here, because of the motor contributions, it's going to see more fault current than the upstream breaker, 3302 breaker. Because of that, the series rating is not applicable in this case, right? So series rating is really limited to branch circuits where you have just lighting or non-motor loads, basically. Okay, finally we're going to talk a little bit about 100% rated multi-case circuit breakers. Okay. As we mentioned before, a standard multi-case circuit breaker, UL 489 breaker, is rated to carry 100% current continuously at 40 degrees C ambient in open air, which you're never going to encounter in the real world. In an enclosure, they must carry 80% of their continuous current rating at the 40 degrees C ambient. So if I have a 100 amp breaker in an enclosure, it can carry 80 amps continuously. Continuous is defined as 3 hours or more. Okay. This is the basis of if you do load calculations per the NEC, that's why you have to take 125% of the continuous load. That works out to be 80%, right? So it's the same calculation. The reason is because of the heat inside of the breaker, the enclosure, limits the continuous current that the breaker can carry. So that's the basic rule. Now if the ambient is lower and maybe it won't trip at 81% or 85%, but that's the basic rule and that's the NEC requirement. So it doesn't really matter what the real world is. You have to follow the code. So, but that's the basic rule. You're limited to 80% of the breaker rating. Now when I get up in the bigger breaker sizes, that becomes a problem, because if I have a 3000 amp breaker, I'm limited 80% of that 2400 amp continuous, but I still have to size all my conductors based on the 3000 amps, not 2400. So because of that, you can buy what they call 100% rated multi-case circuit breakers. Now the 100% rating, the breaker has to be 100%, has to be rated for 100%, but it also has to be within, it's a function of the enclosure size. So if you look at this nameplate for this breaker, it says for 100% application, minimum enclosure size is 28 inches high, 19 inches wide, and 8 inches deep. So you cannot apply the 100% rating unless it's in an enclosure at least that big. Okay. Also, this must have an electronic trip unit, which probably is not going to be a problem for a large breaker. But also, to have a 100% rating, you must use wiring with 90 degrees C insulation applied at the 75 degrees C ampacity. So you cannot use insulation types that are only rated for 75 degrees C. In certain types of equipment, you will not be able to buy a 100% rated breaker. They're not available. So this becomes an economic analysis because of the conductor size issue. Is it cheaper to buy the bigger breaker, the 100% rated breaker, so you can use smaller conductor, or you put in the normal breaker at 80% and just go with the bigger conductor? So it's strictly really an economic analysis. Okay, so last little thing we'll cover, we're running out of time here, is the issue of multi-case circuit breakers and your Arc-Flash calculations. You have an awful lot of your system is protected by multi-case breakers, and so how they perform has a big impact on your incident energy calculations. So almost invariably, if your multi-case upstream breaker is tripping on instantaneous, your arc flash at your protected bus will be low. It may not coordinate very well, but you'll have low arc flash because it's tripping so quickly. If this breaker is tripping on its thermal curve, your downstream arc flash is going to be high because it's going to be so much slower. Okay, so this becomes, and that transition happens extremely quickly, just the width of this instantaneous trip pickup. So sometimes by tweaking that instantaneous trip down 1 notch, you can go from 40 calories down to 0.6 calories just that quickly. So the setting of the instantaneous trip on these breakers becomes a much bigger issue. Of course, this all assumes the breaker is actually going to trip, which is another thing that we talked about in the maintenance. Okay, so we're pretty much out of time, so I'm going to cut it off there. I know we have some unanswered questions, so I'm going to, if you've got questions, feel free to type them in, and I'll try to get to them, as many of them now as I can. But otherwise, we will get a response to you one way or the other, because we'll track these questions. We're going to do an example, but I kind of ran out of time. Well, one thing I want to mention quickly is the fine style. If you go to the low voltage power, the multi-case breaker, when you're defining those, there'll be a fine style button. So if you go to that, you'll bring up this box. If you just type in the first few letters of the style, and hit select, it'll limit the breaker choice because there's so many breakers in there. If you know the style name, I would definitely use the fine style feature. If you do find a breaker that's not in the library, if you send that information to tech support, if you're on maintenance, we'll add that for you to the library at no cost. All right, thanks everybody.